Hello everybody, welcome to this audio slides presentation. I am Muhammad Haidar Sharif. For the next several minutes, I will be discussing the findings of my recent paper entitled A Numerical Approach for Tracking Unknown Number of Individual Targets in Videos. Suppose that we wish to get a comprehensive match of a target in the candidate frame. Immediately a common question will come to pass. Where will we search the target in the candidate frame if the candidate regions are not known to us? One possible answer would be the integral images, which will allow for very fast feature evaluation, but computing a complete set is extremely expensive. With problem size n, brute force search holds asymptotic runtime of O of n factorial, which is impractical to use. To solve this dilemma, a number of automatically generated specific regions called candidate regions in the candidate frame have been proposed. We can search the target from candidate regions only. Based on the shape and size of the track of interest, candidate regions can be represented by rectangles, ellipses, circles, squares, and triangles. But how can we generate candidate regions in the candidate frame automatically? The proposed method in this paper explains how to generate those candidate regions, followed by the techniques of matching and tracking unknown number of individual targets in videos with an asymptotic runtime of O of n q. Suppose that a person is moving in 6 consecutive frames. Foreground silhouettes of the moving person in the consecutive frames can be extracted by equation 2 as mentioned in the paper, and then each frame is converted into the blue channel of RGB color model. The algorithm in listing on takes those frames along with a decay factor delta as input. The complete output of the algorithm is the layered record of motion image LRMI. Assume that upper left figure hints a sample video of PET's 2012 dataset showing current frame number 186. Our aim is to find out the number of possible candidate regions from this frame automatically. Upper right figure represents the created LRMI. For simplicity, the white marked region in the lower left figure will be analyzed. Lower right figure displays the numerical values of the white marked region. Figure of B shows the numerical values of the white marked region with different color codes. Figure of C demonstrates numerical values which are more than 239. Figure of D explains the effect of delta and xi on threshold. Figure of E illustrates segmentation by clustering of the numerical values of LRMI. Figure F shows segments which have pixels more than 5. The areas of miscellaneous segments have been represented by color codes in figure of G, and their estimated boundaries have been displayed in figure of H. The white dots in figure I indicate centroids or whose centers of segments. A total of 165 weak and strong candidate regions can be extracted from the frame number 186. Weak candidate regions should be deleted, but how can we delete them? Phase correlation technique is used to annihilate the weak candidate regions using phase correlation peak. Finally, 75 strong candidate regions can be extracted for tracking. Hungarian method is used to solve the assignment problem, but it fails to reconstruct full trajectories of targets in 3D space. Consequently, Hungarian method along with Kalman filter can solve the existing problem for tracking unknown number of individual targets with an asymptotic runtime of O of nq. Two individual persons tracking results reported by our method using a video of PET's 2012 dataset. 50 individual birds tracking results reported by our method using a flying birds video from web dataset. Unknown number of individual bacteria and RBCs were counted and tracked by our method using videos from web dataset. A numerical approach to count and track unknown number of individual targets in video with asymptotic runtime of O of nq has been presented.